Good afternoon, everyone. I'm Rob Slater from Redshift, co-founder. In this talk, I'm going to briefly introduce our renderer, Redshift, and then I'm going to tell you a little bit about some of the progress that we've made as a company over the last year. So what is Redshift? Well, Redshift is not just another GPU renderer. Redshift is a final frame production quality renderer that brings the features and flexibility of biased CPU rendering to the incredible speed of the GPU while making it viable and practical for professionals. So Redshift was written from the ground up to fully harness the power of the GPU. This means we can render scenes many times faster than CPU renderers and without the usual limitations associated with GPU renderers. And we also have great scalability. We can render scenes and pack tens of millions of triangles in under a gigabyte of RAM with hundreds of millions on 12 gig cards. And with our out-of-core technology, this means we are not limited to the amount of VRAM that's available. This means we can render scenes containing terabytes of textures and billions of triangles without any problems. And we also believe in deep DCC integration. We want artists to be able to use their favorite DCC with Redshift and with all the cool tools available to them without compromise and without a deep learning curve. So 2015 was a great year for Redshift. Probably the highlight of that towards the end of the year was winning the Best New Application category, CG Awards. That was good. And we also had several great reviews. Towards the end of 2015, we saw significant market expansion. Back in 2014, most of our customers were freelancers and small studios. We're talking about 5 to 20 employee studios and smaller projects. But towards the end of 2015, we started seeing larger studios and thus larger projects coming our way. And in 2016, that trend is continuing. Some very big name studios are actually inquiring about us. And we also saw a shift in market types as well. So early on in 2014 and 2015, we were mostly popular for like marketing, previs, architectural, medical kind of rendering. But in 2016, we saw a new type of market, and that's like streaming, Netflix, and Amazon originals. Now these are like feature-length productions. They're all CG, really heavy rendering, and so naturally Redshift seems to be a good choice for them. So regarding Redshift and GPU in the industry, so one of the lessons that we had to learn over the last year is that we still have to convince the skeptics. Now GPU rendering has been around for some time now, but some studios are still kind of like reluctant to adopt it. So some of this skepticism comes from our company itself, like, you know, who are Redshift, and some of the skepticism is about GPU rendering in general. So regarding like Redshift as a company, because we've not been around for very long, large studios want to see how well Redshift does in the industry and you know, what kind of projects Redshift is used for. But thankfully, because of the large studios that have started to adopt Redshift and the large projects that they're doing, some of that skepticism seems to be going away, which is fantastic. And regarding GPU rendering in general, we still get questions about, like, you know, what is the quality of GPU rendering? Does it have lots of limitations? Do you have like missing features? Can you render large scenes? Is it noisy? But thankfully, because of the caliber of the work that's being done by the studios that are using us now, that skepticism seems to be eroding away as well, which is fantastic. So this year, we've started seeing like several big name studios showing an interest in Redshift. And it's almost like a Trojan horse effect. Like what happens is that, you know, they'll try Redshift with some like LookDev or Previs. They'll buy a couple of licenses, and then they'll slowly start to realize that, you know, they can use Redshift on their larger, you know, main productions as well. So what we've seen with some studios is that they've gone from using their CPU renderer with 80% of their rendering to actually using Redshift instead. And hopefully we'll see that trend continue. We're really excited about that. And you know, because we fully believe in GPU rendering, we think it's here to stay. And we are very passionate about it and think that it's going to dominate the industry very soon. So last year we were preparing for our release of Redshift 2.0, which we'll talk a little bit about next. But Redshift 1.0 continued to evolve over the year. So we added a whole bunch of new features. We added round corners. We licensed the technology from NVIDIA, thanks NVIDIA. And it contains all the cool features that round corners gives. There are no tricks. You can handle intersecting geometry, and there's no extra memory or anything like that. And we also added a 3-layer skin shader, very similar to the ones that are available in Arnold or V-Ray. Now, prior to that, we only had like one subsurface scattering shader. It had a kind of a non-intuitive absorption controls, and you would have to blend the three of these things together to get a realistic looking skin. So that was kind of cumbersome and it was slow. So we added the 3-layer skin shader, and now things are much better, and everyone's very happy. We added bicubic texture filtering. Now, this might not sound like a very exciting feature. It can be very helpful for like displacement maps, where you actually want very smooth filtering for displacement. And very importantly, we added a technique called hair min pixel width. Now, what this does is that it says that, you know, very thin hair will actually become transparent the smaller it is on the screen. Now, you can see from this render here, this is a pathological case. So we've got some very thin hair that's very brightly lit. Now, the bottom image shows a render with 1,000 samples per pixel, and you can see that the tips of the hair are still very noisy. You get like this aliasing kind of effect. But the topmost image, we're using hair min pixel width technology with only 64 samples. And as you can see, it renders a lot cleaner, and it actually renders 2 to 3 times faster too. Some other features that we added was that we added support for shaven haircut and XGen hair in Maya. And we added XGen splines as well, with XGen archives coming later this year. And we also added a VR stereospherical camera support, and we'll be adding cubic and other formats later in the year too. And we added support for Linux. Oops. And we added an SDK and Redshift command line. Now, all these features were very important for some of the larger studios. Linux has the advantage of not being hindered by Windows display drivers. And what this means is that Redshift will actually run faster on Linux. This is a bit like the TCC mode that Windows has. The Redshift SDK is being used by some larger studios to integrate their production pipelines and their scene assembly tools like Katana. And Redshift command line allows you to export a scene from Maya and then render it on a machine that actually doesn't have Maya installed on it. So it's like a standalone tool. And also throughout the year, we did the usual performance and stability improvements. So as I mentioned earlier, probably the most important release of this year was Redshift 2.0. And with that, we intend to close the feature gap between CPU renderers and the GPU renderer, and we're almost there. So what have we done? We had multiple dome lights. This feature was requested by many of our customers, so we finally caved in and gave them that. We added light map texture baking support. And we also added an improved technique for subsurface scattering using the improved dipole model. This adds extra realism to an already blazingly fast point-based solution. And to complete the subsurface equation, we added support for single scattering. Now, one new feature that we're very excited about is ray-marched volumetrics. This is like OpenVDB support initially. We'll be talking a bit more about that in detail later. And we added a procedural API as well. This is a bit like Arnold DSOs. This allows you to like send procedural geometry to Redshift, which can then get turned into triangles on the fly. And another important feature that we added was automatic handling of nested dielectrics. Now, prior to 2.0, artists would have to jump through some serious hoops when trying to model overlapping mediums such as liquid within glass. So with 2.0, they no longer have to use the index of refraction ratios for the medium interface. They can use the index of refraction of the medium itself and let Redshift take care of the rest. So one of the things we're adding with 2.0 is a new Redshift material. We'll talk a bit about that next. And to prepare for that, we had to add some new shading technology. So we added support for the popular GGX BRDF, which is favored for its wide specular tail, and also the Cup Torrance old standard BRDF with Beckman distribution. Another thing that we added was physically correct Fresnel for rough reflections. Now, prior to 2.0, as the material would get rougher, the Fresnel effect would stay constant around the silhouette of the material, which was not realistic. So what actually should happen is that as the material gets rougher, the Fresnel effect starts to get flatter. So we implemented that, and we also made it energy conserving as well. So as far as we know, not many Uber shaders in renderers actually do this out of the box. And so with all these cool new features in place, and at the request of an important customer, we were able to then successfully port the popular Arnold shader AL Surface by Anders Langlands. It's our Easter egg, if you like. Okay, some other cool features that are just around the corner. We're soon going to be adding automatic VRAM management. Now this feature is where Redshift will automatically compute the memory budget between textures, geometry, and rays. And this will give you the best possible performance for a multi-GPU machine, particularly where the GPUs have different memory requirements. And after that, we'll be adding custom AOV support per light AOVs, and we'll be improving our subsurface scattering technology by adding ray trace subsurface scattering. This will add extra detail to our ray trace subsurface solution. Okay, the Redshift material. So why a new material? Well, back in 2013, our first DCC integration was with Softimage, and so our first Uber shader, Redshift Architectural, was designed with Softimage and naturally mental ray in mind. Now this material shader, was fairly fully loaded. You could make lots of nice materials out of it, but it did have its shortcomings. And now one of those shortcomings was that while it has multiple reflection layers, they were not very intuitive to use, and energy conservation was kind of difficult to understand. It involved fiddling with weights and all sorts of things, and this just confused artists, so that was something that we had to change. And importantly, it also had a very non-linear glossiness response. This is for reflections and refractions. And this meant that textures were not very portable between different renderers. And with the dawn of PBR-authored textures from like Substance or Unreal, we really wanted to be able to use those assets, so we had to solve this problem too. So just to demonstrate, if you look at this image here, the top row is our legacy Redshift architectural shader using Redshift 1.0. And as you can see, the glossiness fall-off is very non-linear. In fact, it favors the sort of high glossiness. And below that, we've got like Ashman-Shirley, Cook Torrance, and GGX with Redshift 2.0. And as you can see, the glossiness response is about the same, and it's much more of a linear effect. So I think we can all agree that the top one looks pretty horrible. Okay, and speaking of BRDFs, we only ever had one BRDF with Redshift 1.0, apart from Hair, which uses the Martian BRDF. We used to use Ashman-Shirley. Now this is a very efficient BRDF. It cleans up well, but it was not very good for modeling metals like chrome and stuff like that. Now that's where the GGX BRDF wins overall. And speaking of metals, our metal support was pretty lousy all over, right, in Redshift architectural. So we could have added new features, removed some things and changed things or renamed things, but we decided that would just make things more complex. So we had to say goodbye to Redshift architectural and hello to Redshift material. So with a new Redshift material, one of the first goals was to simplify the layout. We wanted artists to be able to like jump right in there and start making cool new materials with greatest of ease and without being like confused by lots of complicated options and things. But power users, don't worry, all the really tricky bells and whistles we still have, but we just hide them in a separate tab away from all the regular controls. Now, just like the Redshift architectural shader, this one comes with two reflection layers, a base and a coating. But unlike the Redshift architectural, they are energy conserving by default, so no more fiddling with weights and things like that, which would make it very much easier to use and more intuitive. The coating layer also comes with a fake transmission control. This is like fake coating thickness, very useful for things like complex paint or tinted glazing, stuff like that. And it also comes with its own bump map input, which is separate from the base bump. So this means you can add things like fine details like scratches on the coating, or even remove bump mapping altogether from the coating. And we also added flexible Fresnel reflectivity controls. So in 1.0, in the Redshift architectural shader, you could choose between whether a material was dielectric or a conductor, meaning a metal. Now, we wanted to make that simpler with the Redshift material, so we kind of unified that. But more importantly, we added a Fresnel control for red, green, and blue channels. Now, this means that you can come up with realistic metals now, and also physically correct dielectric tinted materials, where the actual tint around the silhouette of the material should actually become monochrome. And as well as that, we added a metalness support. This is a feature that users of Substance and Unreal should be very familiar with. And so with this non-linear roughness and the metalness support, this means that the Redshift material is now actually PBR texture ready. So no Uber shader would be complete without subsurface scattering. So we added that too. Just like the Redshift skin shader that I mentioned earlier, we have 3 layers of multiple scattering in this material. It's using the improved dipole model, and it also uses the diffuse albedo to tint it. This means it's easier to do textured subsurface scattering for things like skin and stuff. And we also added single scattering as well to complete the subsurface equation. This is a great technique for doing things like murky liquids and things like that, and fog. And finally, and it has been a long time coming, we added support for dispersion. Now this is the kind of rainbow effect that you get through refractive materials. Now prior to 2.0, poor artists would have to use what's commonly known as the poor man's 3-color hack. You'd have to like blend like red, green, and blue refractive materials together, which can be like cumbersome to set up, and it would be actually quite expensive to render as well. But with the new built-in dispersion, you actually get the full rainbow effect of colors, and it renders faster too. So as mentioned earlier, we added Raymarch volumetrics. Now just to clarify, this is non-homogeneous volumetric lighting. So Redshift has been doing a homogeneous volumetric lighting for some time now, and it works really well with importance sampling. But Raymarch volumetric lighting is significantly harder, and there are lots of challenges that we had to like overcome in order to do it properly. One of those challenges is storage, because GPU memory comes at a premium, and OpenVDB containers can require a lot of memory. That was something that we had to solve. And also kernel execution incoherency. You know, when different rays do different kinds of work, the GPU really does not like that, and it can actually underutilize GPU resources, which means the rendering will be slow. And also we had to solve the problem of importance sampling, meaning how can you use the fewest possible samples and get the cleanest possible result, and thus the fastest render. And finally there was shading. How can you get like really complex shading, really full-featured shading on volumes, but without paying the extra cost of shader switches as the ray travels through the actual volume itself? So regarding storage, well, the solution is actually the same as the solution for CPU rendering, and that's to use a sparse tree. Now this is the same technique that OpenVDB uses, and what it essentially means is that we don't waste memory on empty space. Then there's also quantization and dithering. That's a neat trick to actually compress data. So not all channels in the OpenVDB grid actually require full floating point precision. So by compressing data, what this means is that you can actually store more information on the GPU per voxel than on the CPU. And then there's LOD. Now this is a neat trick where you can actually like reduce the volume grid the further away it is from the camera. Now this means it uses less memory and will render faster. Now regarding execution incoherency, we did a talk about this last year, and the solution is to actually do ray sorting. And what this means is that you can, by grouping all the work together for volumes away from the other work, that means the GPU's resources are utilized at most efficiently, and that means you get actually faster rendering. And Redshift is great at that. Okay, regarding importance sampling. So what we have to do is try and guess where to actually like concentrate the samples to get the best possible lighting. And like a naive solution is to say, well, you know what, we'll concentrate all the samples on the based on grid density. And this works quite well if the light is very far away from the surface. But the problem is if the light is very close to the surface, and you might end up using too few samples on a very thin, non-dense part of the volume and too many samples on a dense part, and you end up with noisy renders, and that's no good. So the solution that we chose, which was pretty difficult to implement, was actually like a little bit like multiple importance sampling. So we use both the volume density and we use the light BRDF to try and choose where to best do those samples. And this is like I said, it's quite tricky to implement, but it does get us very clean results and faster too. So here's a little example with the OpenVDB bunny. We've got a very hot light behind both these things. We've got 64 samples per pixel here. Now the bunny on the left is using just grid-based density as the importance, and on the right we're using our multiple importance sampling. And here's a close-up so you can see the difference in noise. So as you can see, the pure grid-based density importance sampling, you get very noisy results, and on the multiple importance sampling it's nice and clean. I hope you can see that. Okay, and lastly, shading. So shading can be very expensive when your ray is traversing through a volume. You get lots of very heavy context switches. So, you know, how do we actually like solve this problem and get it to render really fast with very nice complex shaders? Well, the solutions was to actually limit the shading capabilities. Now, when I say limit, I mean we actually limited users to be able to use arbitrary shading networks. So instead what we did is we designed a volume material that's fully packed with all like the commonly used features for volume rendering, like tints, we got like value remapping, and we got gradient and color gradient scales. And we got some very nice results from this. And we're probably going to expand it later. So this is just an example of the volume shader. So on the bottom right there, we're using some grid remapping, using a color ramp. It's nice and psychedelic colors, very pretty. Here we're showing the emission remapping, so you get nice looking explosions. Then various absorption remapping, including like a shadow density scale at the bottom there. This gives you like almost the effect of multiple scattering for no extra cost. Okay, so in the future, we're going to be concentrating on adding support for new platforms. Side Effects Houdini has just entered alpha. We're very excited about that. And also Maxon Cinema 4T is just a couple of months away for alpha. We've got lots of people asking support for this. And then we're going to investigate Modo and Katana support. More features that are becoming later in the year. We're going to be adding a shader SDK. And after that, we'll be adding support for MDL and OpenSL. Toon shading, Redshift custom viewport, so this will actually in some ways give you faster renders and also allow you to like view AOVs and things like that in the viewport. We'll be adding support for distributed remote rendering, optimized particle rendering, which means you can have like more particles using less memory, and of course it will render faster, and custom per object shading properties for like things like crowds and things like that. Trace sets, good for power users, barn door lighting, and also XGen instance support and Maya curve support as well. Right, well, thank you for listening. For more information, you can contact us at the email address shown there, or come and meet us right after the talk at booth 377. Thank you.
Thank you very much, Robert. Has anyone got any questions for Robert?
Yeah. Anything about shading? Because I write the shaders.
Okay, well, thank you very much for coming to our talk, and thank you, Robert. It was great. Thanks.